Hello everyone. We continue the journey. The last video we basically stopped at Pascal's triangle. We were introduced to Pascal's triangle, but we didn't really go through it because um, and I did not upload the previous video. I had a problem with the exportation process. In the exportation process, and that's mainly because it was my mistake. I had it render at a high number of frames per second, and then HD and all that crap, which is useless at this point in time. Anyways, so to quickly recap on what we've done yesterday. So we've done a bit of exercises on, so we revisited the basic terminologies, natural numbers, positive numbers, rational numbers, irrational numbers, and then we also talked about the subsets and how the empty list is part of every subset regardless of what that set is. And we've also talked about the order, what the order, if someone says an order in a set, what's that mean, or what's that stand for? So we know that the set is the order is basically the size of the set or the cardinality, and for a finite set then the order is basically finite, and for an infinite set, the cardinality is the same. The cardinality is the same. Sorry. We also came to remember that prime numbers start from 1, 2, 3, 5, and going forward. One thing we noted down here is that the prime numbers are always positive, and the number 1 is not a prime number. Notice earlier I said 1. Well, that was my mistake. I always thought 1 was part of the prime numbers. Apparently, no, it's not part of the prime numbers. And the other terminologies we got acquainted to were the factors. So if you have a number and then you want to get its factors, so all the numbers that you multiply with leads to the number at hand is called the factor, the positive factors. However, the proper factors, remember we mentioned proper sets. So when we say proper sets, the superset has to have an element that's not in its subset. That's when you call it a proper subset. For the proper factors, so you list down so it's usually the number itself and the 1 are always part of the factors that we create or that we have. For proper factors, 1 and the number itself are not considered factors at all. So we have an example here. We've noted it down. So we have 1, 2, 3, 4, 6, 12. These are the factors for the number 12. However, the proper factors, you eliminate the 1 and you eliminate the 12. So you'll be left up with 2, 3, 4, 6. Proper fraction, on the other hand, is, as we've seen in the irrational numbers, rational numbers are fractions that build up proper results, like produce a proper end result. Unlike the pi, where you have 3.14, etc., and infinitive numbers along the line. However, the proper fractions is when you have a numerator which is less than the denominator, like a quarter or a half, so that's like a proper fraction. So if you have, like, I don't know, 5 out of 1, you can just write it as 5. That's not a proper fraction. And what else? If we want to get the number of subsets within a set with x number of elements, then we usually obtain that through 2 to the power of x, x being the cardinality or the order of the set. So given that definition, a set with 1 element is 2 to the power of n, which means 2 subsets. And building up on the knowledge we've learned so far, the 2 subsets would be the element itself and the empty list. And this is where we got acquainted, where we got introduced to Pascal's triangle. Now try Pascal's. I'm not sure if we should really study this, but given we were introduced to it anyway, so we might as well just know a little bit about it. So Pascal's triangle is more like a formula. It's more like um, a visual, maybe if that's the right term, a visual formula that yields. So instead of you using the function to the power of n to get the number of subsets, you could simply use Pascal's triangle to obtain that. Pascal's triangle serves several purposes. Um, so it's not only about the number of combinations; it can serve various purposes. We could look into it, but first let's visit something really quick. So we have here, so this is how Pascal's triangle actually works. So yeah, so we've done also yesterday the exercises introduced in maths is fun.com. So we done the sets and we've done the exercises. The score initially wasn't the best. I had like, I don't know, I had like a 70%. And then I redid the test, the quiz, and I got a good mark, like a full one. But that doesn't matter, that doesn't prove anything anyways. So it's a process of learning, and here we keep going. So so this is how you get basically this in this chapter or this section. They talk about subsets and how they get the number of subsets within a given set. So the 2 to the power of n, we've already like briefly talked about it just a second ago, a few seconds ago. No. So with Pascal's triangle, as you can see, this is how it's. So to build up the Pascal's triangle, you start with ones on the very left hand side. So you build up the ones and then the index 1, 2, 3, 4, 5, 6, 7, and then you basically have. Now I'm not really sure how they got the third row. Oh, triangular numbers. The third diagonal has the triangular numbers. Triangular numbers should be, so if you can see, it's 1, 3, 6, 10, 15, 21. Okay. What's the pattern there? Oh, this is the triangle number sequence, 1, 3, 6. So you got 1, 3 dots, and then you add another 3 dots, and then you got another, you add another dot. So you start off with dots, you add 2 dots every time. No, you don't add a dot every time. 1, 2, 3, 4, 5. By adding another row of dots and counting all the dots. Oh, so you basically just add a dot, add another row every time, adding an extra dot to the end. So like in this case, you had 2, and then so the next one would be 3, this one would be 4, and then the other one would be 5. So those numbers build the 15 dots, and that's how the triangular number sequence came from. Okay. So for each row, you count. So row number 1, you got 1 dot, and for the row number 2, you got 2 dots. And here, 2 dots, 3 dots, 4, yeah, and so on. Okay. If we rearrange the dots, okay, to look nice, then double the number of dots and form them into a rectangle. Okay. Now it's easy to work out how many dots. Just multiply n by n plus 1. So it's n plus 1, 2. N plus 1, 3 dots. So n by, so in this case it's 2 multiplied by 3, you get 6 dots. Can use 6 centimeter dots in triangle n, so we could use the rule. And then you just divide it by 2 because we doubled the numbers here to form a rectangle, so halving it, taking 50% of it, would yield the triangle. So now if we go for 60, then we know that 60 multiplied by 61, and then we divide it by 2. Alright. This is enough ground for you to lay 22 logs side by side. How many logs can you fit in the stack? So it's 22 multiplied by 23 divided by 2. But you can fit 253 logs in it. Okay. So this is what the triangular numbers are. So in this case, this is the sequence 1, 3, 6, 10, 5, 15, 21. Sorry, 10, 15, 21. And going back to the sets, you see there are different subjects that really branches us to different topics altogether. But let's stick with the Pascal's triangle for now. So we know that these are the ones, and then this is the index, this is triangular numbers. And for us to get this subsets of a given set, say for example we have a set of 1 elements, we have 1 subset. If we have a set of 2 elements, then we have 2 subsets. If we have a set of 3 elements, we have 4 subsets. If we have a set of 4 elements, we have 8 subsets. Now, something to keep in mind, this is the first level and this is the second level. What does this mean? Is that, say for example, we have a set of 3 elements. So when you take single elements of the set, you can only form 1. So it's only 1. Then if you take, there are two subsets of is this right? Yeah, there are 2 subsets with 1 element, and then there are 2 subsets of 2 elements, then 1 subset of 3 elements. So what's this mean is that an empty set has just 1 subset in this case. So let's take the example of, let's go along with this, of what's been written here. So there's always one, so the empty list or the empty set is always part of any set. So it's a subset of any subset. Remember, it's a subset of every set. And that means there's only one element of it being empty. So if we have an empty list, then we have only one empty subset. Sorry, I keep saying lists, and I should change the terminology to say sets instead, because that's a bit of confusing. Given the computing background, that's kind of, confusing at times. But let's keep going though for now. So there's an empty set that has one subset. A set with one element has one empty set. So we have one empty subset, and then we have one, so in this case 2 elements in here. Sorry, it's an element of it's an of 1. So we have 2 subsets. One subset being an empty subset, and the other subset with 1 element. Now, if we have a set of 3 elements, so we are on the 3rd level here. So a set of 2 elements. In this case, 1 would be empty, and 2, 1 level subset, 1 element subset, and the second and the third box here would be 1 subset of 2 elements. And that's how we proceed with the rest of the until we have like a set of several 1, 2, 3, 4, 5, 6, 7, 8, until we have a set of 7 elements. And of course, I think this could keep going, I'm not sure, but for now, this is what the Pascal's triangle is saying to us. So what we could do is we could use the Pascal's triangle to actually verify that our work is legit, or we're walking down the right path. So say we're given an element of 5, a set of 5 elements: apple, banana, cherry, date, and an egg. Now we can, using the Pascal's element, know how many subsets we are going to write. So using the formula straight off, using the formula is 2 to the power of n, so 2 to the power of 5, and then we should get the number of subsets. Or the second approach, we could simply go with the Pascal's triangle. Pascal's triangle, in this case we have 5 elements, so we suspect 5 elements to be the 6th row. 0, 1, 2, 3, 4, 5. So this is the 5th. This means 5 elements in a set. So we have one empty list, we have 5 subsets. So we have 5 subsets of one element, and we have 10 subsets of 2 elements. We have 10 subsets of 3 elements, 5 subsets of 4 elements, and 1 subset of 5 elements. Now remember, this is a subset. For a proper subset, we have to subtract 1, which is the last one here. Yeah, and yes, we are right to say that. See, Pascal's triangle, we start from index 0, and then we need to find 10 subsets. You must think harder. Yeah, so it's only 4 subsets, choosing 3 out of 5. So you go row 5, position 3. 0, 1, 2, 3, 4, 5. We should be getting position 3. 0, 1, 2, 3, 4, 5. Yeah, so that's like 10. We should be getting 10 there. You need 10 subsets. Fair enough. So that's generally how they use the connect my charger. So that's generally what Pascal's triangle is all about. It just gives you a visual, fast approach to, instead of using the calculator, you could just simply go opt for the triangle usage. Of course, there are different other approaches, so it seems. Now, of course, Pascal's triangle has other uses as well, so it doesn't have to be. So by going through the documentation here, one of the most interesting number patterns is Pascal's triangle, named after Blaise Pascal, famous French philosopher, mathematician. To build the triangle, you started with ones. So this is what I've explained. You started with ones, then you continue placing numbers below it in a triangular pattern. Each number is the numbers directly above it added together. So in this case it's 1, you add 1, 1, and then so the two numbers are 2, 1, 2, 1, then moving on, 2 and 1, that's 3. 3 is actually, wait a second, what is he saying? Continue placing numbers below it in a triangle pattern. Each number is the numbers directly above it added together. I have highlighted the 1 plus 3 equals 4. 1 plus 3 equals 4. Okay, so this is ones. The next diagonal has the counting numbers. Indexes 1, 2, 3, 4, 5, 6, 7. Third diagonal has the triangular numbers. The fourth diagonal not highlighted has the tetrahedral numbers. I'm not sure what those are, but yeah. Tetrahedral. I think this is the dice kind of number sequence. I'm not sure what importance this brings to the table, but I'm assuming that given it's mentioned, then fitting a stack of marbles, tetrahedron. This shape is called tetrahedron. Count how many marbles are needed for stack certain height. Only on the one marble. We need 4 marble. Oh, interesting. This is really interesting. I think architectural folks would find this quite interesting. I believe they do. I mean, to build something of height 2, you need like 4 marbles. 4 marbles. 1 at the top and 3 below. Okay. Anyways, you need like 4 marbles, and then you need 10 marbles, 5, 3. Okay, I don't think we really have to dive into this. So going back back. Okay. Triangle is also symmetrical. The numbers on the left hand side have identical matching numbers on the right hand side. So yeah, if you look at it, there's 3, 6 is the separating line. Then you have, yeah, I see what you're saying. 20 is the separation line in here. And then, yeah, okay, like a mirror. The horizontal sums, they double each time, the part of 2. Yeah, 1, 2, 4, 8, 16, 32, 64, 1, 2, 8, 2, 5, 6, and so on. Exponents of 11. Each line is also the powers exponents of 11. Okay. Oh, okay. This is nice. Now this is a bit weird though. I think there's a mess. So this one is pointing to a row. 1, 6. So this is 1 to 1. 1, double 3, 1, 1, 4, 6, 4, 1. Then how come is this? I think there's a mistake on this one. It doesn't make, unless the rule be void, that's a different story, right? So it's 11 to the power of 5. It's 161. Yeah, there's a mistake in here. This doesn't exactly prove this. Oh, okay, so this one is. So what happens with 11 to the power of 5? Simple. The digits just overlap like this. What is this? It's like we're forcing it to work. So there's the 5 plus 1, that's 6, and then 0, 1 is actually 1. Oh my god, it's like forcing it to work. And then what's the magic with the 11 to the power of 6? I mean, with all due respect, I mean, you don't really have to make it work. I mean, you could just not state that fact and that's it. I understand that this could be really useful for those who really need the exponents of 11. Who am I to judge, right? Right, so for the second diagonal, the square of number is equal to the sum of the numbers next to it and below both of these. What? For the second diagonal, so we have 1, 3, 6, 10, 15. So we have 4 to the power of 2. Oh, okay, okay. Equals 10 plus 15 equals 25. So it's like this number, which is the square of a number, which is basically just any square in here. It equals the sum of the number next to it and the number below it. So 3 to the power of 2 is actually 3 plus 6. 4 to the power of 2 is actually 6 plus 10. And 5 to the power of 2 is actually 10 plus 15, and so on. Okay, there's a good reason to. Can you think of it as, okay, so whatever. And that's why it's 11th exponents of 11. Fibonacci sequence. Make a pattern by going up, and then along, then add up the values as illustrated. So going up, I'm not sure which way is up to you, but it looks like he's counting. This is 1, and this is 1, and then 1 plus 1, 1 plus 1. So it goes like 1 plus 1. So plus and then 1 next to it. It goes like up and then along. So 1 is actually 1 plus 1. And then for the next one is 1 plus the one at the top along. The next one plus 2. And then 1, 3 plus 1. I'm not sure why they choose 3 here. Then 8 is actually 1 plus 4. Oh yeah, because there's, so you go up along, you keep going up. So 1, there's 1 and there's nothing on top of it, like on top next to it. 1, then 2, going up, there is no third or column here. Over this, you got this at the top, and then 2, next to it is 1. Then 1, next to it is 4, on top of it is 3, next to it is 3, on top of it is 1, next to it is null. 1, on top of it is 5, on top is 4, next to it is 6, on top is 3, next to it is 1, on top of it is nothing. So that's how you do it. That's the Fibonacci sequence. So you add those, you sum this up, and you will have 1, 1, 2, 3, 5, 8, 13, 21, and that is by adding the previous numbers. So for example, 3 plus 5 is 8. So this is 4 plus 1 is also 8, etc. Odds and evens. If you color the odd and even numbers, you end up with a pattern the same as Sierpinski triangle. Oh man. Oh, there's a lot to take in here. But at least we got an idea for the next. I mean, if we ever came across this, we know that there is something out there that uses the Pascal's triangle. So using Pascal's triangle, heads and tails, I'll show you how many ways heads and tails can combine. So this is mostly from the probability, and this something we're not saying quite familiar with, but we kind of got acquainted to this. And I think we will get to know more of this as we progress down the line. I think it's too early to talk about probability now. But anyways, so the same sequence applies. So we have 1, 1, the same triangle applies. 1, 1, 1, 2, 1, 1, 3, 3, 1, 1, 4, 6, 4, 1, and on. So the possible results in this case are 2, 1 possible result for combined elements, and then 2 results for the elements, and then 3, and then the same applies 3. So we got 3 options because we have 3 in the rectangle, and so on and so on and so forth. Now this is heads and tails, and then we have something else called combinations. How many combinations of objects are possible? So this is something what we have. This is something we have talked about a bit earlier in the sets. So the sets basically to reveal the number of combinations we could have as we do. So we have an example here. We have 16 pool balls. So it's like a set of 16 elements within it. So by using the mathematical formula 2 to the power of n, it's 2 to the power of 16. So 2 to the power of 16 would yield 2 to the power of 16 would yield 65,536. 16 pool balls. Oh, so you could only choose just 3 of them. So this is going to be so this is going to be tricky. But using the rectangle, so if you keep going down, way down, 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 we get to the now you can see here, like this is the 16th row, index 16, and then 16, this is an empty element, this is of 1 element, this is of 2 elements, and this is of 3 elements, and this is just 3 of them. This is what it says, 3 of them. So we know it's 560. It's very precise in here. This is quite interesting. Now I think it's very clear what the value of this Pascal's triangle is. If you need to generate a number of combinations and you need to validate them, your only option is basically Pascal's triangle. I mean, it's not your only option, but it's your only best option, your next best option, whatever it is, to validate the number of combinations you could generate is using the Pascal's triangle and use the index to. And remember, you start off with 0, 1, 2, 3, and that's the number of combinations you should expect. All right. Moving on. a formula for any entry in the triangle. In fact, there is a formula from combinations for working out the value at any place. Oh, okay. So instead of us going to the power of n, we could simply use the factorial in here. So it's commonly known n chose k and written like this. So n, so in this case we have n 16 and we choose 3. So n factorial 16 factorial divided by k factorial n minus k factorial. Oh man, notations. So the factorial is basically the multiplication, subtracting the value by 1 each time at each step. So this could also be an actual representation of. This is really interesting. I'm really liking this. So the guy's actually included 14, 15 lines, man. I think it would have helped a lot if you just did 16, just to be easier to visualize the solution in here. Though it's very clear though, and I really don't think it needs more elaboration than that. So you can also show the coefficients in binomial expansion. What is this binomial expansion? Binomial is a polynomial with two terms. Two terms. What the hell is a binomial? Polynomial. It's a polynomial. A polynomial looks like this. It has three terms. Polynomial is like basically a function. It's a polynomial. You have a constant variable, exponent, whatever it is, and the binomial is a polynomial with two terms. Okay, so but can the two terms be something else? Okay. I think we could just skip this one for now. We don't have. So we know polynomial is the form, is a function. Show you the coefficients. Okay, 1, 2, 1, 1, 3, 3. Oh, okay. The power of 4, and oh man, this is amazing. We should write that one down. Should write that down. Alright, so that's an example there. We should remember that example for a good period of time. Okay, this is actually really nice. Should have it in reference here for a subsets. No, this is Pascal's triangle, so we should reference this instead. Pascal's triangle. Several terminologies introduced here, which is something really nice. Polynomial function. Alright, so that's that with the Pascal's triangle. I think we've went through a good chunk today, though it would have been nice to do more maybe. Yeah, I think we should do more. Anyways, I'm stopping this video for now. Let's continue maybe later. Alright, cheers.